In this section, we introduce a new structural element, the linear spring, and examine the relationship between springs, cables, and bars. We also discuss the role played by spring elements in the solution of statically indeterminate problems. A spring is a structural member that deforms when it is subjected to a force. Our primary interest will be in linear springs, those springs whose deformation is proportional to the applied force. Many springs are coiled structural elements, as shown in this figure in the upper right, and are represented schematically by the sawtooth-shaped symbol shown here, an approximation of how the helical spring looks when viewed from the side. Many structural elements exhibit spring-like behavior, at least when loaded over a limited range, and this enables cables, ropes, bars, and other structural elements to be modeled as springs. In this section, we establish a quantitative relationship between force and deformation among mechanical elements. We will let L0 be the initial length, that is to say, the unloaded length of a spring. If the spring is subjected to an axial force F sub s along its length, it stretches a displacement delta. If the spring is linear, the stretch is proportional to the applied force, and the force-displacement relationship follows the straight line shown in the figure at left. The constant of proportionality is often designated by the symbol K and is defined as the spring constant. Spring constant K has units of force per unit distance, so in the systems of units we've been discussing, in English or US customary units, this will typically be either in pounds per foot or pounds per inch. And in the SI system, this will have units of newtons per meter or perhaps newtons per millimeter. The larger the value of K, the stiffer the spring, that is, the smaller the stretch for a given applied force. If the spring is elastic, the spring returns to its original unloaded length L0 when the load is removed. For any real material, this means we cannot apply an arbitrarily large load to the spring. This is something you can easily demonstrate for yourself using a delicate spring. Many clickable ballpoint pens, for example, are spring-loaded. They are designed to remain elastic under the loads you can apply with your thumb and under the range of motion between the clicked, that is deployed, and unclicked, that is withdrawn, states of the pen. If you disassemble such a pen and hold the spring between your fingers, you realize quickly that you can easily apply an excessive load that unravels the helical pitch of the spring and leaves it permanently deformed. This implies that our linear force-displacement relationship is just a model and is only expected to be valid up to some threshold force not shown in the figure. In addition to being linear and elastic, this spring is also isotropic, that is, it behaves the same way in tension as it does in compression. Structural elements are not guaranteed to be isotropic, but many are, and we will assume in our applications that this is the case. On occasion, we may use the opposite sign convention for our linear elastic spring, usually when the spring element's principal service mode is in compression. Here the initial unstretched and final stretched lengths are reversed in the definition of the spring law, but you can also see from the graph of F versus displacement delta that nothing substantive has changed. The first and third quadrants of F versus delta have been flipped between the current and previous slides, but that's about it. One other point we'll make is that the force that's carried by the spring will be aligned with its deformed geometry. In a minute, we're going to look at this problem involving an electrical switch, and we could push the switch from some location near the vicinity of C towards some other location near the vicinity of D. As we do so, the orientation of the spring will change quite dramatically from being nearly vertical to being quite slanted. The force that will be carried by the spring will have a line of action that is defined by the points A and B. So as the spring is deformed and stretched, the orientation of the force carried by the spring will always be carried with its deformed geometry. In this example, we have a model for an electrical switch and are asked to determine the force F needed to cause the switch to make contact at point D. It would be more precise to ask for the force required for the switch to be on the verge of making contact at D, because that is the threshold force for contact. In this case, a free body diagram of the switch will not include a contact force at D, since the question presumes the switch is on the threshold of contact. We are also told to assume bar CD is frictionless, so the reaction force between the switch and bar CD will consist purely of a normal force, and if we use a traditional XY coordinate system, that means the reaction force will be purely in the Y direction. Because bar CD is frictionless, there's no resistance to pushing the switch from C towards D, and therefore there is no horizontal force component to the reaction. We might also note that the spring has a 7 millimeter unstretched length, and the smallest stretched length that it will have is when A tends to be right over B. What that tells us is that throughout the entire motion of the spring, it will always be in tension. Its least tensile state will be when A is directly over B, and it will become increasingly tensile as we push it towards D. Our free body diagram then for the switch will look like this. We'll note that in this stretch state, the angle theta is here, and that's equal to 40 degrees. We're going to cut through the spring force, and because it's always in tension for the conditions given in the problem statement, I'll represent that as pulling on the switch. Here's my force F sub S. I also have the force F as a result of my pushing it, and the figure is a little misleading because it shows a force F and it also shows a finger pushing the switch, which sort of suggests that there are two forces tending to make the switch go to the left. In fact, the force F is meant to be the result of pushing on the switch. So we have just the force F as we try to move it from in the vicinity of C towards the vicinity of D. And then finally we have just this normal reaction force, since CD is given as being frictionless. We could write our force equilibrium equation in the x direction as minus F plus the spring force sine theta equals 0, and that gives us that F is equal to the spring force, which is K L minus L0 sine theta. And we can see from the figure that L is equal to 10 millimeters over cosine theta, and for theta equals 40 degrees, this ends up being 13.05 millimeters. So if we plug in K as half a Newton per millimeter and L as 13.05 millimeters, L0 as 7 millimeters, and theta equals 40 degrees, we get a value for F that's equal to 1.946 newtons. We could also write a force equilibrium equation in the y direction, and that would allow us to get the normal force N, but I'll simply stop here. In our second example, we want to specify the characteristics of a spring incorporated into a pogo stick. The characteristics are specified based on a range of weights we might expect for the smallest and largest children to use the stick. We're to specify the stiffness K and initial length L0 of the spring so that the stick begins to compress when 50 pounds is applied and is fully compressed when 200 pounds is applied to the footrests. So here we have the pogo stick in its disassembled form and consisting of three pieces. On the left, we have the pogo stick housing, then we have the spring in the middle, and we have the piston with step on the right-hand side. We begin by noting that most of the child's weight is evenly distributed on the two footrests, with only a small fraction of the weight applied to the handlebars. For our purposes, we will assume all the weight is on the footrests and consider the limiting weights given in the problem statement of 50 and 200 pounds. So to begin, I'm going to move this from this location to this location, half on each side, and I will also show that in the separated pieces here. Now the stick housing is also subjected to a compressive force from the spring, and that's going to push upwards right here, and there will be an equal and opposite force on the spring here. The spring is in compression, so it's also experiences a compression force here, and the equal and opposite force on the piston step then is here. Generally speaking, there will be contact between the piston and the bottom of the housing of the pogo stick, so I will include a force F sub P here generally to represent that, and then there's an equal and opposite force here on the piston. And finally, we'll note that we've got the weight W at the bottom of the piston step here. Note that if we reassemble all these pieces back into the pogo stick, we're going to get a cancellation of equal and opposite forces between the various components. And what we will be left with then is the half the weight on each footrest and the total weight reacted down here at the bottom of the pogo stick. So in these free body diagrams, the weight is some arbitrary value, and F sub P represents the force between the piston and the pogo stick housing. As per the specifications in the problem statement, at a weight of 50 pounds, we assume contact is broken between the stick housing and the piston, and F sub P goes to 0. At this weight, vertical equilibrium of either the stick housing or the piston gives spring force 1, which is K times L0 minus L1 is equal to weight 1. And in this equation, we don't know spring constant K or unstretched length L0 yet, but this is a case for a specific value of L1, that is 9 inches, and W1 equals 50 pounds. Also per the specifications in the problem statement, at a weight of 200 pounds, the spring is fully compressed, meaning the housing is now on the verge of making contact with the step built into the shaft supporting the piston. The significance of that is it tells us that the stretched length under this condition is 9 inches minus 5 inches, or 4 inches. So now we have a second spring force, which is K times undeformed length minus deformed length equals W2. But here, L2 is 4 inches and W2 is 200 pounds. We're getting a little crowded, so I'll use the space up here to continue the solution. Our two unknowns are the spring constant K and the undeformed length L0. I can take the ratio of these two equations, and the spring constant K will disappear, leaving me with L0 minus L1, so L0 minus 9 inches, divided by L0 minus L2, which is 4 inches, equals the ratio of the weights, which is 50 over 200 pounds, or 1/4. So I could write this as L0 minus 9 equals 1/4 of L0 minus 4. And so I can rearrange that as 3/4 L0 equals 8 inches, or L0 is equal to 10.67 inches. I can then substitute that back into either of my equations to get the spring constant K. So for instance, I could write K is equal to W1 over L0 minus L1, which would be 50 pounds over 10.67 minus 9 inches, and that turns out to be 30 pounds per inch. If you like, you can do the same thing with the second equation, that is, write K equals W2 over L0 minus L2, and you should find you get exactly the same spring constant.